Welcome everyone. In this video, we're going to learn how to find horizontal asymptotes. So for horizontal asymptotes, let me start off by showing you a picture. Let's suppose you have an arbitrary function that looks like this. So, maybe like that. Something like this. Let's just go with this picture. So call this y equals f of x. Or you might have something like similar to this graph. Let's say so take a look at these two pictures. And of course, we can break them down into more cases, but let's start off with something basic. So horizontal asymptote is computed by simply taking the limit of that given function as x goes to plus and minus infinity. So as x goes to infinity, if you look at this one, it looks like the function is getting closer to this line right here, which is the x-axis. So the horizontal asymptote will be y equals 0. And here, if you go to negative infinity, so as x approaches negative infinity, the function is just going to probably keep on going down, or we don't know. It doesn't have any horizontal asymptote on the left side, but on the right side, it looks like the function settles to this line right here, eventually as x gets very large. So that's one way to look at. Another way to look at is, take a look at the second image. So as x goes to infinity, so as we let x gets large, the function will settle to maybe whatever that number is. So you can call it y approaches some number L. Let's call it that. And then on the left side, maybe the function will settle to this number right here as x approaches negative infinity. So as x approaches negative infinity, we can say the function is approaching this number right here. So it's pretty much, we can identify horizontal asymptote by taking the limit of a function as x goes to infinity or negative infinity. So this will be the definition for finding horizontal asymptotes. Now let me write down more precise definition of it. So we have three different cases. So 3 cases for horizontal asymptotes. So one, let's consider if your function is a ratio of 2 functions. So let's say if your function f of x happens to be a polynomial over another polynomial, then the horizontal asymptote will be computed by the following. So you pretty much take the limit as x approaches plus or minus infinity of p of x over q of x. And if the degree of the top, which is p of x, is greater than the degree of the bottom, which is q of x, then we say that the horizontal asymptote is none. There is no horizontal asymptote. So we can say then there is no horizontal asymptote. Now, if we switch around the inequality right here, let's say the second would be if the degree of the top is less than the degree of the bottom, then we say that the horizontal asymptote is always y equals 0. So the function will always go to 0 if the top is less degree than the bottom function. And the last case we're going to write down is what if the degrees are equal. So the last case we can summarize as if the degree of the top, which is the p of x we're saying, is exactly equal to the degree of the bottom, which is q, then the horizontal asymptote is their leading coefficients. So these are the three different scenarios we can run into when it comes to computing horizontal asymptotes. So let me show you a couple more examples using these different cases. So for these three functions, we're going to find their horizontal asymptotes. So let's do the first one. So we're going to compute the limit as x approaches plus and minus infinity of 3x plus 7 over x squared minus 2. So if you look at the degrees, so the degree of the top polynomial is 1, because this is the one we're looking at. The power of x highest is 1. And the degree of the bottom function is right here. That's the highest power. So that's going to be 2. So the top degree is less than the bottom. So that means when you take the limit as x approaches either plus or minus infinity of 3x plus 7 over x squared minus 2, you're going to get 0. Now, if you want to use the method we discussed in another video, which I'll provide the link below, you pretty much take the highest power in the denominator and divide everything by that term. So if I do that here and try to show it 0, so I have the limit as x approaches plus and minus infinity, 3x divided by the highest power on the bottom, that's this one. So you get x squared plus 7 over x squared over x squared over x squared minus 2 over x squared. And then we simplify. So the limit as x approaches either plus or minus infinity. I'm putting them both in the same question because it wouldn't matter. You'll do the same work for both plus infinity or minus infinity. So we have 3 over x simplifies, and then 7 over x squared, that's just 7 over x squared. And on the bottom, you have 1 minus 2 over x squared. Now, as you take the limit, this goes to 0. This goes to 0. This is 1, so that limit is 1. And this limit is going to go to 0. So what we have is simply the limit as x approaches plus or minus infinity of, well, those limits are 0. So really, I don't have to write this anymore. So we have 0 plus 0 over, and limit of a constant is just constant minus 0. And that's simply 0. So that's why if you just compare the degrees, you know that this limit right here will give you 0 because the bottom is growing much faster than the top. Now let's go ahead and find the horizontal asymptote for the second problem. So this one right here. So we're taking the limit again as x approaches plus and minus infinity of 2x cubed plus 7 over x cubed minus x squared plus x plus 7. Now here, if you compare the degrees, so the degree for the top polynomial, so that's this one right here, is 3. So that's the highest power we see. So the degree is this one. Well, we can call it 3. And then the degree for the bottom polynomial, it's going to be this one. That's the highest power. So that's also 3, which means the horizontal asymptote for this one, it's going to be y equals their coefficients. So this is the coefficient of that term. And for x cubed on the bottom, the coefficient is 1. So it's their ratio 2 over 1. So the horizontal asymptote is y equals 2. But we want to show that work by simply applying calculus. So we take the highest power on the bottom and divide everything by that term. So we know the highest power is x to the third. So we have the limit as x approaches plus or minus infinity. So 2x cubed over x cubed plus 7 over x cubed divided by x cubed over x cubed minus x squared over x cubed plus x over x cubed plus 7 over x cubed. And now if you simplify this, you will have the limit as x approaches plus and minus infinity 2, because this cancels out, x cubed. And the second one doesn't simplify, so just rewrite. And on the bottom, we can simplify x cubed over x squared is 1. And then x squared over x cubed, that's 1 over x. Plus x over x cubed, that's 1 over x squared. And the last one, 7 over x cubed. Now let's take the limit as x goes to plus or minus infinity. Now eventually this will go to 0. This will also go to 0. This will also go to 0. And this will also go to 0. And the limit of the constant is just this constant right here. So therefore, the limit of this function is simply 2 over 1. Or we can say 2. So our horizontal asymptote is this number, y equals 2. That's the horizontal asymptote. And now let's work out the last problem we have here. So we want to find the horizontal asymptote for this function. So we will do the same thing. Now let's look at the degrees. So if you compare the degrees for this one, the degree on top happened to be, so the highest power is right here. So it's 3. And the degree of the bottom is going to be this one right here. That's the highest power, 2. So the top is greater than the bottom. So that means it can go to either plus or minus infinity. So there is no horizontal asymptote. So no horizontal asymptote. But let's see if it goes to plus infinity or minus infinity. So here you want to separate the limit into 2 different limits. You take the limit as x approaches infinity of x cubed plus 7x squared minus 2 over x squared minus x plus 1. And you take the limit as x approaches negative infinity of x cubed plus 7x squared minus 2 over all of that, x squared minus x plus 1. The reason we didn't have to separate for the previous 2, because either way it's the coefficient of their leading power or 0. But here it could be either plus or minus infinity. So you want to split it up into 2 separate limit problems. Now let's go ahead and do the same thing. We take the highest power of the bottom and divide everything by that highest power. So I simplify the first one, the limit as x approaches infinity. So you do x cubed over x squared, 7 plus 7 over x squared minus 2 over x squared, all over x squared over x squared minus x over x squared plus 1 over x squared. And you'll do the same thing here. Divide everything by the highest power in the denominator and take the limit as x goes to negative infinity. So let's just focus on the left limit. So if I simplify, I get the limit as x approaches infinity. So I have x for the first term. The second one is 7. And the third one is going to be 2 over x squared. Over the bottom, I get 1 minus 1 over x plus 1 over x squared. So you'll get the same thing when you simplify the one on the left side. Now let's take the limit as x goes to infinity. So as x goes to infinity, well, this limit is just constant. So the second one, we have, so the limit as x approaches infinity of x plus the limit of a constant, that's just the constant. And this limit right here, that's going to be 0 because x is infinity on the bottom. So we have minus 0, let's say that, over. Now the bottom ones gives us, we have the limit of a constant, that's 1, limit of 1 over x, that's going to be 0, and 1 over x squared, that's also going to be 0. So all of this will give you just the limit as x approaches infinity of x, because the limit of a constant is simply 7. So as x goes to infinity, this limit is just going to grow to infinity. Plus 7, well, it doesn't matter what constant we're adding or dividing by. In this case, it's 7. So the limit is infinity. Therefore, we said there is no horizontal asymptotes. Now, if you try to do the same thing with this limit right here, you do the same thing we did for the left limit, and you will eventually end up right here. So now substitute negative infinity. So let me show you how to do that. So the procedure is the same as the infinity limit. For negative infinity, you simply now take this and substitute negative infinity in here. And then you take the limit. So as you plug in negative infinity, this just a constant. This will go to 0. This will go to 0. And this will also go to 0. So what we're left with is simply the limit as x approaches negative infinity of x plus 7 all over 1. So, and you can ignore that if you want to. And this is going to give you the limit as x approaches negative infinity of x, because limit of a constant is just that constant. Now, as I plug in negative numbers into x, this limit goes to negative infinity. Adding 7 to it wouldn't make any difference. It's still going to go to negative infinity. Therefore, this limit has, it's negative infinity, so there's no horizontal asymptote. So that's what we concluded earlier. If the degrees of the top is greater than the bottom, when you take the limit approaching plus or minus infinity, you'll get either infinity or negative infinity, which means there's no horizontal asymptote.